Picture a massive, highly advanced military machine flying deep into heavily fortified enemy territory. No alarms trigger, no radar pings. It slips right through. This scenario is a daily reality. This is the practical application of stealth technology. Modern airspace functions like a tightly woven net of invisible electromagnetic tripwires, using overlapping sensors to monitor every inch of the sky. Standard aircraft struggle in this environment. A traditional fighter jet acts as a giant, loud, and incredibly hot target that broadcasts its position to enemy screens from miles away. Survival in modern combat requires a multi-million-dollar machine to vanish from these tracking systems entirely. Stealth technology mathematically erases an aircraft's physical, electromagnetic, and thermal signatures to hide the machine from modern sensor networks. Ground-based radar systems represent the first major threat. These large rectangular mesh antennas constantly sweep the sky with radio waves to hunt for targets. This diagram shows the standard radar mechanic. Radio waves bounce off a target and return directly to the receiver. Stealth aircraft change this interaction. The geometry deflects the incoming radio waves, scattering them in multiple directions so they never return. The F-117 Nighthawk pioneered this design. Notice the sharp, faceted geometric plates shaping the nose and cockpit, specifically angled to scatter incoming signals. Modern stealth evolved into the flying wing design. The completely smooth, flat underside of the B-2 Spirit eliminates highly reflective vertical surfaces that traditional radar easily spots. Maintaining this geometry requires a clean exterior. These open internal weapons bay doors on the F-35 hide missiles and engines deep inside the airframe. This structural shaping physically shrinks the radar target, but a secondary layer of defense is needed to handle the remaining electromagnetic signature. Engineers apply specialized radar-absorbing materials to the outside of the aircraft as a second defense layer. This animated cross-section illustrates the process. The chemical coating acts like a sponge, drawing in leftover electromagnetic energy and dissipating the energy inside the material instead of reflecting it. This coating is extremely fragile. A single scratch can compromise the entire defense, which is why these machines require constant, highly classified maintenance. Infrared sensors represent a separate threat, tracking the extreme heat generated by jet engines. Cooling systems solve this problem by mixing bright red engine exhaust with freezing atmospheric air before it leaves the jet. This produces a cool purple or gray trail that vanishes on heat-seeking sensors. By layering geometric shape, chemical material absorption, and thermal masking, engineers systematically erase its physical footprint. This erasure is a constant technical struggle. No aircraft is ever completely invisible to every possible sensor. Detection systems are evolving, using low-frequency radar, satellite surveillance, and AI-based tracking to try and find holes in a stealth aircraft's defense. Stealth technology reduces a target's signature to the point where a machine becomes nearly impossible to track and target at range. This difficulty has shifted the focus of modern warfare. Success now favors precision and calculated design over sheer numbers or overwhelming firepower. This design philosophy is expanding. Notice the stark, angled, wave-deflecting hull of this naval destroyer, applying aviation stealth principles to maritime fleets, drones, and space platforms. Modern strategy favors the force that can operate entirely unseen, controlling the battlefield before the enemy even knows a target is present. If you enjoyed this look at the science of stealth, like the video, subscribe to the channel, and hit the bell icon so you never miss an update.